Okay, what we're going to do now is we're going to talk about the common ion effect in regard to slightly soluble salts. We talked last time about KSP and how these are used to quantitatively describe how soluble a salt is. So before we were just talking about one salt into water and how many ions those would produce. What we're going to be looking at now is what happens if you have more than one salt. Let's say, for example, we have a mixture of two salts. How would that affect the solubility? So we will talk about Le Chatelier's principle here. That is relevant. Again, we've talked about that before. But Le Chatelier's principle helps us predict which direction the system will shift, whether it's towards the left or to the right. In this example, we're talking about adding sodium sulfide to a sample of lead 2 sulfate. So sodium sulfate to a solution of lead sulfate. So obviously it is that sulfate ion that is the common ion. And if we add more, we would expect that equilibrium would shift to the left to use up those excess sulfate ions. So additional sulfate ions causes that shift to the left, and it will decrease solubility. Here we have an example of strontium fluoride. The KSP value is given. We're going to look at the solubility in pure water and then the solubility in other solutions that contain a common ion. So let's go ahead and start. We can do an ice table here. And I don't include the solid. We start with 0. This is going to go up by x and up by 2x because of that coefficient of 2. And so the concentration of strontium was represented by x and of fluoride is represented by 2x. Our KSP expression would have strontium and fluoride, and that would be squared. If we substitute our values for x in there, we would have x for strontium, we would have 2x for fluoride, and that would be squared again. So what is KSP in terms of x? It is 4, because it's 2 squared is 4, and then all of our x terms here would be x cubed. That is equal to the KSP value, which is up here at the top, 7.9 times 10 to the negative 10. So, of course, I'm going to want to solve for the value of x. This is my solubility, which I use x to represent that. So divide both sides by 4. So I have that x cubed would be equal to 2 times 10 to the negative 10. And then if I cube root both sides, x would be equal to 5.8 times 10 to the negative 4 molar. And this is our concentration of, our molar solubility here. Now, let's look at what would happen if we have a solution of strontium nitrate. So strontium nitrate, the nitrate ion is a spectator ion. It has no acidic nor basic behavior. It doesn't form a precipitate. So it's just there. It doesn't do anything. So I'll show you how this is going to affect our results. So again, we don't have any of the solid at equilibrium. Now our strontium concentration, strontium is present, and it says it's 0.1 molar. There's just one of that. So our initial value of strontium is 0.1 molar. We don't have any fluoride. So if you then would just kind of follow along, we're going to do the calculations from here in a similar way. So up by x, up by 2x. And now we have 0.1 plus x is our concentration of strontium, and fluoride is still 2x. So again, we're going to go back and plug into our same KSP expression. I'm still using the same one. So I'm just going to skip to that next step here where I substitute into that. So this is going to be 0.1 plus x for my concentration of strontium. And for my concentration of fluoride, it is 2x squared. Now, we've seen something like this before. If you think about how we would solve this, you know that the mathematics would require a quadratic equation or something like that to solve for x. What we would assume, if you look up here, the value of x is pretty small, times 10 to the negative 4. If you added something like that, times 10 to the negative 4, to this 0.1 value, it doesn't change it. It is negligible. So we are going to assume that X is really small in comparison to 0.1 molar. So again, this is now 0.1 times 4x squared. Whoops, I gotta fix that. Will give me 0.4x squared is equal to my KSP. So that's 7.9 times 10 to the negative 10. I'll divide both sides by 0.4. Obviously that cancels here. And the value that I have calculated earlier, well, actually I didn't calculate that earlier, the value that I have for x, once we take the square root then of both sides, x is equal to 4.4 times 10 to the negative 5 molar. So let's think about what we see here. 4.5 times 10 to the negative 10 is our molar solubility in this example. So previously it was 5.8 times 10 to the negative 4, and now it's, whoops, I keep hitting the wrong thing. Sorry, guys. Now it's 4.4 times 10 to the negative 5. So why is it lower? So with a common ion effect, we would expect that if we are adding more strontium into this solution, that the concentration of strontium goes up, it's going to shift to the left. And on the left-hand side, we have our salt. So if it shifts to the left, that actually lowers the solubility of our ions. So it makes sense that the value would go down for solubility due to the addition of the common ion. The next example that we're going to look at here is where we have a common ion. In this case, it's not sodium ions, those are neutral, but we have additional fluoride ion present. So setting up our ice table once again. We don't have any strontium ions, but we do have 0.4 molar of fluoride. Oops, gosh, I have to fix that. So if I'm adding these two up, 0.4 plus 2x is the concentration of fluoride at equilibrium. So I am plugging into that same KSP expression that we had in the past. So strontium is represented by X. And fluoride here, I'll plug that in, 0.4 plus 2x, and that's going to be squared. All right, let's look at our math here. So previously, we made the assumption that x was going to be small, and so we could ignore it. And if we do look at the value of x was 10 to the negative 5, so indeed, that is a fair assumption. Here, we're going to do the same thing, where we're going to ignore 2x, because in comparison to the magnitude of 0.4, it's negligible. So we'll go ahead and finish our calculation here, assuming that 2x is small. When we take 0.4 squared, we get 0.16 times x. So our KSP value is 0.16x, or it's equal to that. And then I'll divide both sides by 0.16. That's going to cancel, and that's going to give us x. So x in this example is 4.9 times 10 to the negative 9 moles per liter. So x really went down here. So here's our three values. Let's take a look at what we know. Originally, when we had our solution in pure water, try a blue highlighter here. The solution was in pure water. Our value for x was 5.8 times 10 to the negative 4. Then we added that same salt added a solution of strontium nitrate into our salt, and it caused a shift to the left. It lowered the solubility. In the example that we have, third example here, where we have a solution of sodium fluoride, we added some common ion, which in this case was fluoride. And again, it causes a shift to the left. and it's going to lower solubility. And indeed, the the solubility dropped to 10 to the negative 9. It is indeed quite a bit less soluble as that value becomes smaller. All right, the last thing that we're going to talk about here is what if the thing that we add is acid or base? So it's not necessarily a common ion, but it is something that could affect our solution. So when we are looking at this, pH changes in this case can occur if we add an acid or a base, and we're going to be looking at how this would affect specifically acidic or basic salts. So pH changes will not affect the solubility of neutral salts, nor will they affect the solubility of neutral ions. So I have 3 salts here for us to look at, and we're going to just chat about these quickly. So first of all, sodium fluoride will break apart into sodium ions and fluoride ions. And we think about, do these have acidic or basic behavior? So sodium, that is a neutral spectator ion, so that doesn't do anything. We could go ahead and ignore it. So this, if you recall, F- fluoride is the conjugate base of the weak acid, AHF. So we're going to think about that. So it's a conjugate base. So now we're going to talk about what would happen if I added hydrogen ions to this solution. So this is going to be what would happen if I added a strong acid. So acids are going to react with things that are bases. So obviously the sodium ions do nothing, but it's going to react with fluoride. So what would happen is H plus in fluoride would form HF. So what that would do is it would lower the fluoride concentration. And if that is the case, if we lower fluoride concentration, which way is it going to shift? If you said that it was going to shift to the right, you are correct. Okay, it shifts to the right because the concentration of fluoride is decreased. So adding an acid to a basic salt, that's really what we have here is a basic salt, is going to cause equilibrium to shift to the right. If we were to add a base to this, it is going to have no effect. Okay, it's going to have no effect to solubility. So when it was an acid, it increased the solubility because it shifts to the right. Okay, next thing that we're going to look at is what happens if we were to do the same thing, add an acid and a base separately to this solution of ammonium chloride. So if you recall, chloride is a neutral ion, so that has no acidic nor basic behavior. And ammonium is the conjugate acid of the weak base, NH3. So if it's a conjugate acid, this is an acidic salt. Now, just as a heads up, acidic and basic salt properties is a topic related to Unit 8. And so we would have covered Unit 8, which is acids and bases. All right, so here we're going to be talking about what would happen if we add acid. Well, this is an acidic salt, so if we add H+, there's going to be no effect on solubility because the salt is acidic. If we are now going to talk about what happens as we add hydroxide, that will have an effect. So if we add hydroxide is going to go in there and it's going to react with NH4, ammonium ions. What's going to happen is it's going to form NH3 and then water. So it's going to actually lower the concentration of ammonium because they get used up in this reaction that I've written. So if it lowers the concentration of ammonium, it's going to shift to the right. So it's going to shift to the right, and that actually makes this more soluble. So it increases the salt solubility. Okay, so that's kind of the idea here. It's going to lower the concentration of ammonium, which then is going to cause a shift to the right. I don't know what that is. Causes a shift to the right, which increases the salt's solubility. Okay, last example, and I'm kind of don't have much space here. So sodium chloride, we know that is a neutral salt. So this is a spectator ion, this is a spectator ion. So it doesn't matter. It's a neutral salt, so there are going to be no changes to solubility. Oh, solubility. Spelling is hard. Okay, so just to recap quickly here, we talked about the common ion effect and how that can cause the reaction to shift. If we add a common ion, typically it decreases solubility. We did a calculation for 3 substances. It was pure water versus a strontium solution versus a fluoride solution. And when there was a common ion, indeed, the solubility did decrease. Mathematically, we could see that. And then the last thing here is that we talked about what would happen if we added acid or base, and we again saw that there was a change in solubility. In this case, adding acid affects basic salts, and adding hydroxide affects acidic salts. Otherwise, there are no changes to solubility. Thanks much.